Okay, guys, we're going to learn something new today. We're going to start graphing sine and cosine as functions. So instead of sine and cosine just being a ratio or an operation that you do on the calculator, it's actually a function where the angle is the input value and then the answer you get is the output value. So put in a number for x, get an answer out for y, or f of x if it's in function notation. So when it comes to graphing it, you can pick values for x, like let's say you chose pi over 4, which is the same thing as 45 degrees. You type it in the calculator, you get 0.707, and you decide to plot that point on a graph. Kind of a weird thing to think about, pi over 4, comma 0.707. But you know, pi is 3.14. If you think of it as 3 over 4 is 0.75. So this is kind of like the point 0.75 comma 0.707. And you could certainly plot that, and then you pick another point and another point and another point and then plot them and you get a graph. Same thing obviously for cosine. We won't be plotting points and working things out on a chart, though. We'll use Desmos. That's why you see it on the side of the screen here. So notes before we get started. Both of these are often called sinusoidal graphs. Sinusoidal graphs. They are periodic functions. They are periodic, meaning they repeat the same pattern from negative to positive infinity. So it's not like a parabola or any other type of graph you might have done, a straight line where it just sort of goes. It's a shape, and it repeats that shape over and over and over, carbon copy the same thing every time, and that shape is a wave. In fact, you may have heard the term sine wave before. Any of you who've ever done anything with electronics may have worked with something called an oscilloscope, and you get a sine wave out of that. But literally, the type of wave you can see on water is a sine wave. Okay, so there's some general facts. I mean, if you're sitting at home taking notes, that's great. You can certainly go back, pause, write things down if you want to. But I'm going to go ahead and get right to the exercises. Now I'm going to do number 1 and then 2 and then the rest of the evens, and I'll leave the rest of the odds for you for homework. So we're going to start just by graphing y equals sine of theta. This is the theta axis. You could also say y equals sine x, and that'd be the x-axis, same thing. But before we get to it, I'm going to go to Desmos. I'm going to hit the little wrench up here. I want to make sure that I'm in radians. And then you see here in the middle, x-axis step. I'm going to tell it to make the step pi. Since we're doing everything in radians, look what that does. It gives me increments of pi on the x-axis. Instead of counting 1, 2, 3, 4, 5, here I got pi over 2, pi, 3 pi over 2. Just like on the unit circle, pi over 3, pi over 6. You can have all of these different measurements if you zoom in or out from negative infinity to positive infinity. So again, hit the wrench, make sure you're in radians, and then the x-axis, make the step pi. The y-axis you don't have to mess with. Don't change anything about that. Okay, so I'll hit the home button, and I'm going to type in y equals function trig sine of x. And there you see in that red graph is a pretty funky, crazy wave. It goes through the origin, it goes up to the point pi over 2 comma 1, goes through the origin again. Here, let me kind of zoom in. Down there, 3 pi over 2 negative 1. Oh, every time I touch the screen, all those points go away, so I better not do that. So there we have this. So let's plot some of these points. 0, 0, pi over 2, 1, pi 0, 3 pi over 2 negative 1. Let's see, I'm kind of getting lost here. 2 pi 0, that point up there, 5 pi over 2, 3 pi. And so just, however you can, sort of freehand a curve. I don't expect perfection. anything but a zigzag. Don't draw straight lines. That's amateur. You don't want to look like that. But make it look like a wave. Kind of do arrowheads in those directions. And there it is. That is our first sine wave that we've drawn. So that's y equals sine of theta. Now, there are a few parameters that go into sinusoidal functions. One is called amplitude. Amplitude, here, let me zoom in a little, use a highlighter. Amplitude is the distance from the highest point to the midline. So there's a line that sort of goes through the center of the wave, the line of oscillation, different names for it. And that's the same as the distance from the midline to the lowest point. So for a regular sine function, the distance from here to here is 1, obviously. So the amplitude of a regular sine wave is 1. The period length is a horizontal width. The amplitude is a vertical height. Period length is horizontal. So if we start at the origin, I did not mean to do that. We start here and we trace along the graph. Where do we get to the point where the wave is going to start again? And it's going to be right there. From this point, we have the same old wave, and then it starts again. So the period of this wave from start to finish is 2 pi, which, as you know, 2 pi is 360 degrees. That's one complete circle. So a sine wave, a full wave, the length of it is the same as the angles, the total angle measurement of a circle. So like one trip around the unit circle is one cycle, and that kind of makes sense. Now let's go over and graph cosine. So delete this. Y equals function cosine x. And again, you see a wave, but this time it doesn't go through the origin. It sort of starts up there at 0, 1. And then it goes through pi over 2, 0, pi negative 1, 3 pi over 2, 0, 2 pi 1, 5 pi over 2, 0, 3 pi negative 1, and it just cycles over and over. So we have a little bit of an arc here, curve there, back up, curve, 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 and then it sort of just goes on to infinity. Same thing over here on the left. I draw a little beginning of a curve and an arrow, and that wave cycles from the left to the right forever, just this wave up and down, up and down, up and down. The amplitude of cosine, as you can see, is also 1. The distance from top to middle is 1. Again, top to middle is what we call the amplitude. So not top to bottom, top to middle. The amplitude here is 1. The period length, if we start here at this point and travel along this wave, where do we get to the point where it repeats? And the answer, once again, is 2 pi. The distance from end to end of one single wave, again, is 2 pi. So on this paper, we are going to be using Desmos to graph the given equation, and we're going to tell what the amplitude and the period length is. Because when you start throwing numbers in here and messing it up, that changes the graph, and that changes the amplitude, that changes the period length. So let's look at number 4. We're going to graph y equals 2 sine of x. Now you might, guess right now before you see it, what is this 2 right here going to do to the graph? How is it going to change what you might call a regular sine graph? So I'll type it in. We'll see. Y equals function, nope, not yet, 2 function sine x. And what do you know? It's still a wave. It still begins at the origin, but the height of the first peak of the wave is all the way up to 2. It goes through the x-axis again at pi, and then at 3 pi over 2 it reaches a low point of negative 2. And then it goes through that 2 pi again, and then 5 pi over 2 is another local maximum point. At 3 pi it's going to go through the x-axis, and then we can draw our little arrows here. And this is the graph of y equals 2 sine of theta. So what's the amplitude? Distance from the highest point to the middle or from the lowest point to the middle. Either way, you get the same answer. The amplitude is 2, which, I wonder if that's a coincidence, or I wonder if that's the way it's supposed to be. What is the period length? If we start at the origin and travel along this wave, when do we get to a point where it repeats? Right there at 2 pi. So the period length seems to be unaffected by this 2, but the amplitude is definitely affected by that 2. Let's look at the next one. Y equals 1/2 cosine theta. Y equals 1/2 function cosine x. So calculator uses x, we're using theta. Let me zoom in a little on this. And where does that wave start? 0, 0.5. Then it goes through the x-axis at pi over 2. At pi, it goes down to negative 0.5. What's special about 0.5? Let's see. 3 pi over 2, 2 pi up at 0.5 again, 5 pi over 2, 3 pi, it's down here at 0.5 again. So I'm going to draw sort of a gentle rolling wave. The curves are very gradual. If this was water, this would not do much to rock your boat. So, what is the amplitude of this graph? High point to middle is 0.5, or 1/2. Period length, if we start here and trace our way along the wave, we get to this point before it starts repeating again. So the period length, once again, is 2 pi. So it appears that if you put a coefficient in front of the cosine or the sine, that alters the amplitude, and it is a direct one-to-one relationship. But it does not change the period length. I wonder what changes the period length. Could it possibly be a number in front of the theta? Well, let's look. Let's graph y equals function cosine 2x. And I'll hit the home button again. Ooh, look at that. Actually, I'm going to reorient it just a little bit. Okay, where does the wave start? 0, 1. Goes through the x-axis at pi over 4. Has a minimum point at pi over 2, negative 1. Goes through the x-axis again at 3 pi over 4. Has a maximum point at pi, 1. 5 pi over 4, 3 pi over 2 is a minimum, 7 pi over 4 is the x-intercept again, 2 pi, there's another maximum, and so we get more waves packed into a smaller space, or into the same size space, I guess, however you want to say that. The amplitude is the same. The distance from the highest point to the middle of the wave is 1, and that makes sense because there is no coefficient there. But multiplying theta by 2 did something to the period length. If we start here and trace, we get to the point of repeating the pattern there. The horizontal distance from here to here is pi. The period length is pi, or 3.14, or 180 degrees. Now, you can do this all in degrees, but then, you've got 180 marks just to get to here, and then 360 just to get to there. So normally, you don't graph in degrees. All the graphing is done in radians. That's just fairly standard. Okay, number 10. Sine of pi over 3. Now I'm going to go out on a limb and say the amplitude is 1 because there is no number here. But let's look for sure. Y equals function sine. Instead of theta over 3, I'm going to do x over 3. And look at that. That is a really long wave. So 0, 0, there's a point. 3 pi over 2, comma 1. Where's 3 pi over 2? Well, this is getting a little complicated. At 3 pi, comma 0, there's that. And then out here at 6 pi, we have that. And then at 9 pi. So the points don't really line up really well with the graph paper we're given. The x-intercepts do. So I went ahead and plotted the x-intercepts. Now let's think about this. Here is 0. Here is 3 pi. Between 0 and 3 pi, halfway, is 3 pi over 2, right? Half of 3 pi is 3 pi over 2. So if we split this in half, right there is going to be our high point. Which means if we split this in half, we're going to get our low point. And split this in half, we get our high point again. And this little line doesn't matter too much. So our given graph paper isn't really segmented the x-axis in a way that's all that helpful to us, but we can use some reason to get through it, some logic. So from 0 to 3 pi are two x-intercepts, therefore halfway in between is where that maximum point is, right there that you see blinking on and off. Okay, let's talk about amplitude and period length. Well, clearly, like we said, the amplitude, the height of this graph is 1 unit. Well, the height from the center to the high point or from the center to the low point. Amplitude is 1. Period length, let's start tracing. If we start here, where does this wave start its shape over again? It starts right here at 6 pi. So the period length is 6 pi. Now, maybe you can formulate a relationship between that number and that. Maybe you can't. That might be the sort of thing you learn about in a future lesson, like maybe tomorrow. But for now, you can just sort of look at the graph and count and answer the questions that way. Right, let's look at number 12. Y equals 3 cosine of theta over 3. Y equals 3 cosine x divided by 3. And here we go. So a starting point right here, 0, 3. X-intercept, 3 pi over 2. That doesn't really help a lot. We've got a minimum point at 3 pi, negative 3. That's down here. So maybe we can do the same trick where we split it in half, and that's where the x-intercept is. The next high point is 6 pi, 3, and halfway in between there is another intercept. The next low point is at 9 pi, negative 3, halfway in between. And now we have the makings of this graph. Just sort of draw in some curves. Mine aren't perfect. I don't expect perfection either, just ballpark it. And there's our sine wave. And if I mess with the Desmos a little bit, it kind of takes on that appearance pretty well. Okay, the amplitude, 3. Oh, goodness. That's going to sound great. I hope you weren't wearing headphones. Sorry about that. Okay, so the amplitude is 3. That is the distance from the highest point to the midline. The period length, if we trace along this function from here to there is where it repeats, and it's 6 pi again. So, 6 pi. Number 12 shares something in common with the number 10. They were both pi over 3. Yeah, one of them was a sine, one of them was a cosine, but apparently divided by 3 does something to make it into a 6 pi period length. Number 14. Y equals 1/2 function cosine 2x. Wow, look at that. Now, our graph really only extends to 2 pi, so I can do this so that my Desmos screen goes from 0 to 2 pi. The highest point is going to be right here, 0.5. There's an x-intercept at pi over 4. There's a low point at pi over 2, negative 0.5. 3 pi over 4, pi. So now maybe you can just see, oh, there's a pattern here. I can just sort of draw these dots in fairly quickly and then trace over them, connect the dots, not with straight lines, connect the dots with curves. We want it to look like a wave. And there's our graph. Okay, so now let's answer the questions. What is the amplitude? The amplitude, 1/2. You can say either you're measuring from 0.5 to the midline, or you can just say, well, it's right there, it's 1/2. The period length, if we trace along this graph, where does it repeat itself? Right there. That's where the wave starts all over again. So the period length is pi. Okay, how are we doing here? Are we close to being... Oh, yes, we're almost to the answer key. Number 16. Now, look at number 16. Can you make any predictions? Can you tell already the amplitude? That's that's the easy one. Hopefully you got that figured out. Can you tell the period length? Do you know what having a 3 there is going to do? Maybe, maybe not. All right, so let me type this in. Y equals 2 cosine 3x. Wow, that's a crazy graph. Let me hit the home button. Okay, I don't like that. I want to go from basically 0 to, where does this end? 2 pi. So my graph, that's a fairly decent window to look at. Let's start checking out some points. So there's a maximum point at 0, 2. X-intercept at pi over 6, but pi over 6 isn't one of our options. So let's hold off on that idea for a minute. What about this minimum point? Pi over 3, comma, negative. Where's pi over 3, for crying out loud? Oh, heck. What's going on here? All right, pi over 2, comma, 0. Let me get rid of that. There's at least an intercept here. Let's see the next intercept. 5 pi over 6. That doesn't help. Ooh, goodness. So we're getting into some crazy business here. So between these 2 points, which actually do align to the graph paper we have, we need to find out where to plot those 2 points. Well, basically, we want to split it into thirds. Well, let me see. I'm getting a little carried away with myself here. I'm tapping too many things. So pi over 2, 0, there's 2 more points. There's this one down here and that one down there. So if we split this into thirds, what we're going to have is another x-intercept here and a minimum value there. So pi over 6 is right about here, and pi over 3 is right about there. I might be off a little, just sort of ballparking this. But you kind of do what you can do, Are there any other key points we can lock on to? Let me clear off those points. So let's see. With that maximum point, 2 pi over 3 doesn't really fit anywhere yet. All right, pi negative 2. There's another point we can sort of lock onto. So in between this intercept and this low point, we've got a high point and an x-intercept. So a high point and an x-intercept. We can kind of go like this, this, and this. Let's see. What did we just do? We got there 3 pi over 2. There's an x-intercept. If we split this space into thirds, we've got another x-intercept, another maximum, and then there, and then at 2 pi, there's a point up there. So if we split that into thirds, we're going to have a low point down here, an x-intercept right there, and that. So we're just kind of guesstimating fractional values. But this is what we have. This is what we've got to work with. So the amplitude, clearly 2 like hopefully you've learned to expect. The period length. If we trace from here to there, that is where the graph repeats itself. Now that's a point that I just kind of estimated, so I'm going to go back to the Desmos screen. I'm going to tap these 2 points from maximum to maximum, and this point, oops, let me do it this way. This point here appears to be 2 pi over 3 comma 2. So 2 pi over 3 is the period length. So tomorrow we're going to get into the nuts and bolts of how you actually evaluate the actual, where does this number come from, basically, is what we're going to look at. For now, we're just using the graph to kind of answer that question. So try the odds as best you can, doing what I did, use Desmos. On each and every one, I want you to not only draw the graph, but tell what is the amplitude and what is the period length. If you want to abbreviate, go for it. If you're doing this on this actual document, then the graph paper is right there. If you're doing this with pencil and paper, just do your best to sketch out the graph, however you can. If you have graph paper, that would be great. If you don't, just be very, very careful on your notebook paper. Or try to do this on Notability if you can. That would be really helpful. And then don't forget to check your answers and submit it. So good luck. Text, or not text, but email if you have questions. And hope you have a great day as you go through this.